Well, hey guys, I'm making you guys another video podcast, and I hadn't really intended to, but I got an email today that some of you guys were having some trouble with number 4 and 5 on homework 1. And so here I am, I'm in my hotel room, I got a few hours, and I figured I'd sit down and make one for you and see if we can get it to make sense for you. So that's what we're doing here. So this is going to be I'll just start with 4 on the homework. 4A and B, and then we'll do 5A and B as well. Okay? So, oops. Here we go. Wait a second. Where's my get my brush up here? Okay. This is homework. What the heck is it? Homework 5-1, right? 5-1. Number 4. Okay? Alright, we have an electron in a cathode ray tube. Now, first of all, it doesn't matter what that thing is. A cathode ray tube is really, you might say, a tube TV or maybe a tube monitor, and electrons pass through it and make the image on the screen. But regardless of what it is, it's an object that is moving horizontally at 2.10 times 10 to the 9th centimeters per second. Okay? So initial velocity in the x direction, come on now, is 2.10 times 10 to the 9th centimeters per second. All right. Now, the final answer for A is time, and the final answer for B is displacement in centimeters, so we shouldn't have to worry about converting centimeters to meters. Okay, everything's going to stay in centimeters, so we're not worrying about that right now. Okay, so that's our initial velocity in the x direction. What else are we told about this? Well, we have a deflection, or what makes cathode ray tubes work is it deflects or it accelerates an electron beam up or down or left or right and makes an image. So we have a deflection causing an upwards acceleration. So the acceleration in the y direction, all right, this is in the vertical now, is what? 5.30 times 10 to the 17th. My goodness. Centimeters per second squared. Okay, that's our acceleration, and it's in the y direction. It's not in the x direction. So the question is, what else do we know? Oh, okay, in A. Okay, so that's all we're told at the outset. And the question is, how long does it take to cover a certain horizontal distance of 6.20 centimeters? Okay, so the x displacement is 6.20 centimeters. All right, well, we have an initial x velocity, VIX, we might say. And what is it? That's 2.10 times 10 to the 9th centimeters per second. And we have an x displacement. Now you might say, okay, well, wait a minute. What about that y acceleration? Doesn't that affect it at all? And the answer is no, it doesn't. It's in a different direction entirely. So all we care about is how long it takes for the electron to move a horizontal distance of 6.20 centimeters. All right? So if you recall that velocity, that is the generic equation for velocity, is displacement over time. To solve for time, that means that time equals displacement divided by velocity. In this case, it's all in the x direction, so you might want to put Vx right there. So let's simply solve for time now. Let's solve for how long it takes to go that horizontal distance, 6.2 centimeters, at that velocity. All right? So that is 6.20 centimeters divided by our initial velocity. That is 2.10 times 10 to the 9th centimeters per second. Okay, centimeters cancel out. The seconds winds up being our only unit, and so we have an answer in seconds, and that will equal to be what? That'll be 2.95 times 10 to the times 10 to the negative 9th seconds. Now, it's anything times 10 to the negative 9th. That means to the fraction of that exponent. So you might say 10 to the third is 1,000. Well, 10 to the negative third would be 1,000th. Well, 10 to the 9th is a billion. So 10 to the negative 9th is 1/billionth. So we've got 2.95 billionths of a second. So this thing is moving pretty fast, as electrons tend to do. But regardless, this is our answer right here. 2.95 times 10 to the 9th seconds. Again, the y component of movement, that is the y acceleration, doesn't affect it at all. It's still moving at the same velocity in the x direction because there's no x acceleration. All right, that's A. Let's do B right here. I'm going to write B up at the top. Okay, question is, what is the vertical displacement during this time? So you might say delta y is what we're trying to find. Oops. Or you might say yf is what we're trying to find. That is y final is what we're trying to find. Remember, y or delta y is simply y final minus y initial, and if our initial y position we just call 0, then y final is the same thing as delta y. So really, how much does it move upwards in this amount of time? Well, this is the amount of time it takes for it to move horizontally. But this amount of time also applies to the y direction. So let's write time over here. Time equals 2.95 times 10 to the negative 9th seconds. And what else do we know about y? We know the acceleration, right? Acceleration is right here. Acceleration in the y direction is 5.30 times 10 to the 17th centimeters per second. Okay, and we want to find, again, this right here, this is our y displacement. By the way, is there any initial y velocity component? Well, we're not told that there is. It's simply moving horizontally, and so that means there is a 0 velocity component. Initial velocity in the y direction equals 0 meters per second. So it's not moving up and down at all when it starts accelerating. Of course, it does later, but the initial velocity is what the I stands for. Initial velocity in the y direction is 0. And this will be very helpful because we can use all of this now. Time, acceleration, initial velocity, to solve for our displacement. How do we do that? Well, this is our equation 4 of kinematics. That is, our displacement equals initial velocity times time plus 1/2 times acceleration times time squared. Okay, well, this makes it even a little bit easier because since our initial velocity in the y direction is 0, and that means that whole section drops out. So that means our delta y, that is our y displacement over that amount of time, is equal to 1/2 times the acceleration in the y direction, which is what? Acceleration in the y direction is 5.30 times 10 to the 17th centimeters per second squared. That should be a squared right there. Times our time squared. Time is 2.95 times 10 to the negative 9th seconds. That value squared. This should give us our displacement in the y direction. So what is that? 1/2 times 5.30 times 10 to, etc., times 2.95 times 10 to the 9th, etc. What is that? We multiply it out, calculate it, we get a y displacement of 2.31 seconds. Alright, so that's our y displacement, and that's our b. So hopefully that helped you. It's pretty straightforward. It's simply a matter of continuing to try these problems and use the equations that we know. This equation here that I pulled out, that's nothing new, but it's a matter of applying it. So this is homework 5.1, number 4, A and B. I hope that helps you. I'll catch you on the next one. See you then.